So I think maybe the simplest answer is theta will always be 270 degrees plus or minus the angle of the incline from horizontal. So, and this is the angle that's usually given, you know, if that angle from horizontal is 30, it's always going to be 270 plus or minus 30. And so really the main thing you have to do is just figure out whether it's going to be 270 plus 30 or 270 minus 30. In this case, it's oriented this way. The weight force is straight down, right? And I think the easiest way to do this is just draw the coordinate system at the tail of the vector. Draw the negative axes. This is the key axis, the negative y-axis. That's the 270 axis. And you're trying to figure out whether you have to go farther counterclockwise to get to the weight vector or not as far. Okay. In this case, you're going from the positive x-axis counterclockwise all the way this way. You get to 270. You still haven't hit the vector, so you have to keep going. And so in this case, it's 270 plus that angle of 40. So it's 310. Does that help? Okay. Yes. So the normal force is always, yeah. So the acceleration vector is always going to be A0. The normal force vector is always going to be 0n. Okay? You disagree? Not if the wall's up and down. If you rotate the coordinate system the way I said. So if the y-axis is going out of the surface, then this is always true. I would, yeah. I would recommend doing that, yep. Even if it's upside down, I would recommend flipping the coordinate system all the way upside down. So the y-axis is pointing down and the x-axis is pointing to the left. Okay, so there's the weight. Here's the normal. And then we add 250 this way. So Newton's second law says 0n. Whoops. This is, the weight force is 490.5. What are the components of this 250 Newton force? Yep, that's pointing in the negative x direction, so negative 250, 0. The weight force, what's 490.5 times the cosine of 310? And 490.5 times sine of 310? 375? Negative 375? Thanks. So 314.965 negative 375.362. And then what's that equal to? 50, the mass, yep. Times the acceleration vector, A0, yep. So we have 64.965 is equal to 50A. And N minus 375.362 is equal to 0. So this gives us that A is equal to 64.965 divided by 50. 1 point, what is it? 1.32, okay. 299, so on, meters per second squared. So the acceleration vector is equal to 1.299 meters per second squared, 0. So what direction is that acceleration vector? Is it accelerating up or down the ramp? Down, yep. The positive x direction is down the ramp. We had a positive acceleration, a positive x acceleration, so it's accelerating down the ramp. So this 250 Newton force isn't quite enough to counteract gravity. Any questions about that? Okay, we're going to do one more. Oh, let me do the example the two examples that you mentioned. What about this? I think, yeah, I think there is something to be said for having a consistent pattern that you can apply to every problem, Yeah, I guess that is why, yes. Okay, what about this? Surely you wouldn't rotate the coordinate system for this problem. Yes, I would. So the y-axis points out of the surface. That means the x-axis points this way. And so what would the weight force be? What would be the angle for that weight force? 180, right. It's in the negative x direction, so 180. Or you could just recognize that its only non-zero component is going to be a negative x component. And so it's going to be negative mg 0. But you certainly wouldn't rotate the coordinate system for this. You'd have to be mad. Yes. So the y-axis goes this way. That means the x-axis has to go this way. And so the weight force, your normal force goes like this. The weight force goes like this. And so what are the components of the weight force? In this case, it's 90. Or you can just recognize that it's in the positive y direction. So it's going to be 0 positive mg. And then in that rotated coordinate system, what's the normal force? This is the payoff to all this. 0n, just like it always is. It never changes. And then what's the acceleration vector? A0, like it always is. Okay, that's the benefit of doing this. Any questions about that? Okay, there's question? No? Okay. Over here? Okay. Oh, yeah. So just put this rotated coordinate system origin at the tail of the vector. And then go counterclockwise from the positive x-axis. In this case, it's 180 degrees, or it's in the negative x direction. And over here, you're going from the positive x-axis to the vector. So in this case, it's 90 degrees. And so you can do it as mg times cosine and sine of 90, or you can just recognize that it's a positive y component, so it's just going to be 0 positive mg. Yep. Yeah. So this one actually would have to have something holding it up, otherwise it, would just fall off. So let's say that this force is 300 newtons. Then you'd have 300 here in the free body diagram. So Newton's second law would say 0n plus, okay, what are the components of this 300 Newton force? Yeah, it's in the negative y direction, right? Or else the angle, if you put the coordinate system at the tail of this vector, would be 270. So you get 0, negative 300 plus 0 mg is equal to the mass times A0. You can see from that, as long as it's not falling off the ceiling, the way I drew it, it's not going to be accelerating at all because you have 0 is equal to ma. That's because there are no horizontal forces pushing it side to side, and the ceiling keeps it from accelerating up. The one over here, the normal force is the way it always is, 0n. Mg is in the negative x direction, so we have mg 0. Those are the only forces, and that's equal to the mass times the acceleration a0, like it always is. Yes, thanks. Any questions about that? Okay, the last thing we have to put in this kind of problem is friction. So what happens if there is friction? You can break friction up into two different types. The first one is called static friction. That's when there's no sliding. And when there is sliding, it's called kinetic friction. So sliding is present. Static friction provides the force, whatever force is required to prevent motion up to a maximum value of the normal force times this coefficient. It's the Greek letter mu. And I'm going to write this as mu sub s for the static. It's called the coefficient of friction. So the static coefficient of friction times the normal. The kinetic friction is just equal to a coefficient of friction, this time sub k for the kinetic coefficient of friction times n. The coefficient of static friction is always bigger than the coefficient of kinetic friction. And so what that says is when something is at rest and it's not sliding, the maximum force that can be provided by friction is bigger than when it is sliding. And that goes along with experiences that you've had, like, if you have a big box of stuff that you're trying to slide across a wood floor, a box full of books or something, it's a lot harder to get it moving than it is to keep it moving. That's because the maximum force that static friction can provide before it sort of breaks free of all the attachments is bigger than the friction provided in sliding, the kinetic friction. That's also why the idea behind anti-lock brakes or pumping your brakes, you want, like, your brakes are working through friction force, and you want that friction force to be as big as possible. And so you don't want to start your tires sliding. Once you start your tires sliding, you switch over from this static coefficient of friction to a kinetic coefficient of friction, which is smaller. And so you want to keep it static. Even though it's rolling, it's not sliding, so you're still, as long as it's rolling at the speed that you're going, you're dealing with static friction. Okay, static friction, we're not going to deal with this. That's just sort of a concept I wanted to mention, but this is the one that we're going to do calculations with. So the kinetic force of friction is a force vector the first thing, so any force vector you can break up into a direction and a magnitude. The direction is opposite the direction of motion. In other words, opposite the velocity vector. And the magnitude is the coefficient of kinetic friction times the normal force. Okay, this thing about the magnitude of the friction force being some number times the normal force. That's something you also have experience with, you know, if, so you can imagine this surface is pretty smooth. It's probably not going to take too much force for me to move this along the table, right? That's what you would guess. But what if like an elephant was standing on it and I tried to slide it? Like your intuition tells you that it's going to be harder to make it move, right? If it was frictionless, it would be hard to make it accelerate very much, but it wouldn't, like any amount of force you applied would make it accelerate. The reason that you couldn't get it moving with an elephant standing on it is because that increases the normal force between the notebook and the table. And then you multiply that normal force times this coefficient of friction to get the friction force. So that friction force would be really big. Okay. And how do you get the coefficient of friction? So the coefficient of friction depends on the two materials that are in contact. And it's just something you look up, or, you know, now you just Google it. Google coefficient of kinetic friction for wood and steel. Okay. And it'll give you the coefficient of friction between a smooth piece of wood and a smooth piece of steel. Any questions about any of that? So now here's an updated list of stuff that's always the same. The things that so far we know are always the same. The normal force is always 0n. And the acceleration force is always a0. What directions are possible for the velocity vector if you have something sliding along an incline? Like, so first, not with vector components or anything, but if this box is sliding along this incline, it's not going to jump off the surface. It's not going to sink into the surface. So the only two possible directions are down the incline and up the incline. Okay. And we chose that as our x-axis, right? So the only possible directions for the velocity vector are positive and negative x. And that means that the only directions possible for friction are positive and negative x. They're always going to be the opposite one that the velocity is. So now the friction force is going to be plus or minus coefficient times that normal force, and then the y component is going to be 0. Any questions about that? Let's just do a couple example problems. So let's say that we have an incline of 20 degrees. And a box is on this incline with a force pushing it into the incline of 100 newtons. Let's say that the mass is 10 kilograms. And let's say that the box is sliding down the incline at the instant that we're calculating. Okay, so that's the direction of motion. In the rotated coordinate system, which way is the positive x-axis going to go? Up or down the incline? Up, yep. So there's the y-axis. There's the x-axis. The free body diagram, there's a weight force of 98.1. Then there's a normal force. Oh, and sorry. So this time we're going to do it with friction. And let's say the coefficient of kinetic friction is 0.1. You could make problems where you had to solve for that, but almost always it's given. Right. Yep, that's exactly right. Okay, so the free body diagram, we have the weight force, the normal force, that 100 Newton force. The only thing we don't have yet is the friction.
Is that friction unit newtons?
The coefficient of friction?
Yeah.
Well, the force, the units are newtons, yeah. The coefficient has no units. And you can see that from the fact that this whole mu sub k times n has to be newtons, and the normal is newtons, so the coefficient has to be nothing. Okay, which way is the friction force going to act in this problem? It's going to act up the incline because the motion is down the incline. And so that's going to be 0.1 n. The 0.1 is just the coefficient of friction. I just substituted it in. Okay, so Newton's second law. Can someone tell me what the components of this? So 98.1 times cosine of, oh, well, what's the angle? Yep, 250. So 270 minus 20 in this case. What is it? Okay. And what's the other one? And to figure out whether this is plus or minus, 270 plus or minus 20, draw the coordinate system, origin at the tail of the vector, draw those negative axes, and you can see that to go counterclockwise from the x-axis, you don't make it to that 270 dotted line. So it's 270 minus 20. And then you have 0, negative 100, 0, n. What are the components of the 0.1 n? Why are you nodding and no one said anything? Oh, okay. You said the right thing. Good job. 0.1 and 0. I thought you were like supporting like a boycott or something. and the mass is 10. The acceleration is a0. All right, so now we have to solve a system of two equations for two variables. It's a little different than it was before. In all the problems before we had friction, we could just ignore the y equation if the problem didn't ask for a normal force specifically, and just use the x equation to find the acceleration. Now we have to use the y equation to find n, and then plug that n value into the x equation. You see that? So, the second equation says n is equal to positive 192.18. And here's something that should always be a red flag if you don't get this. Your n value should always be positive. Okay. An n value that's negative means that the floor is pulling the thing down. Okay. Yeah. And now this value, 192.18, gets substituted into the n that's in the x equation. So the x equation says negative 33.55 plus 0.1 times n, which now is 192.18, is equal to 10a. Can someone calculate this? Negative 33 plus 19.2. 14.33 or something like that, is equal to 10a. So a is equal to negative 1.433 meters per second squared. And so the acceleration vector is negative 1.433 meters per second squared, 0. So is this object speeding up or slowing down? Is the friction speeding it up? Is the friction enough to slow it? Friction never speeds anything up. That was a stupid question. Is the friction enough to slow it down, or is gravity speeding it up down the incline? Yeah, this is negative, so the acceleration is down the incline, the same direction as the velocity, so it's speeding up. Okay, so friction wasn't enough to overcome the effect of gravity pulling it down. So considering that, what would you expect if there was no friction? Would you expect that acceleration magnitude to be bigger or smaller? Bigger, because gravity's trying to accelerate it down the hill, friction's trying to slow it down. So if you get rid of the friction, it accelerates more down the hill. Any questions about that? Okay, let's do one more. So let's say there's a box being held against the wall with a force of magnitude 707.1 newtons, acting at 45 degrees. And let's say that it has a mass of 10 kilograms again. And let's say at the instant shown, it's sliding up the wall. What's the acceleration vector? The y-axis is going to point out of the wall. That means the x-axis has to point up. There's a weight force of 98.1. There's this force of 707.1. There's a normal force this way. And which way does the friction force? Oh, and I need to give the coefficient again. Let's make that 0.2 this time. Which way does the friction force act? Down, because it's always just opposite of the motion. So that's 0.2 times n. So Newton's second law says negative 98.10, that's the weight force, plus 0n. What are the components of the friction force? The friction force is in the negative x direction, though, so negative, yep. So negative 0.2 n 0. And then the last one, you could figure this out by putting the tail of the coordinate system, the origin of the coordinate system at the tail of the vector, finding this angle, it's 315. So 707.1 times cosine of 315 is positive 500. (707.1) times the sine of 315 is negative 500. And then this is all equal to the mass times A0. The second equation says that n is equal to positive 500. So that's good. We want the normal force. We want that variable n to come out positive. And then we're going to plug that in to the first equation. So we have negative 98.1 minus 0.2 times 500 plus 500 is equal to 10a. So what do we have here? Negative 1.9 plus a positive 1.9. So I think 501.9 is equal to 10a. Is that right? 501.9 is equal to 10A. So A is equal to, is that right? Which one? Yeah. Oh, those are both negative. Oh, okay. So what is it? 30. Okay. That's still a crazy acceleration. I guess that's just a really big force. Okay, positive 301.9. So the acceleration is 30.19 meters per second squared. So plug that into the acceleration vector and you get 30.190. So is it accelerating up or down the wall? Up. And so is it speeding up or slowing down? Speeding up because it's in the same direction as the motion. Any questions about that? Okay. This? That's why I chose this 707.1. So when you take that times the cosine of, yeah. Any other questions? Okay, so I guess next time we'll do a couple example problems. So in this little segment that I call items normally brought up at the beginning of the lecture, exam 3 is a week from today. So I'll look at the practice problems. I think we'll pretty much go up through the material that we did tonight, but I'll get that up posted on D2L tomorrow, what's going to be on the test. So anyways, hopefully you'll have plenty of time to work on that. Also, exam 4 is the week of Thanksgiving. So it's going to be the Monday and the Tuesday before Thanksgiving. And so there's not going to be any new lab that week. It's just going to be makeup labs. And I'm going to cancel the night class and the night lab. So if if not having, so the Wednesday, right. So you'll have the test on Monday and then no class or lab on the night before Thanksgiving. So think about, like, if you really need that that makeup lab, we can figure out another time for you to do it. But okay, that's it.
Does Monday